Okay, so hi, welcome to the first Project Explained Physics video for AP Physics C Mechanics. Today we're going to be talking about vectors, calculus, and kinematics. Just some brief information before we start the lesson is that this unit in AP Physics C Mechanics does use quite a bit of vectors, including vector operations, dissolving vectors into components, addition and subtraction of vectors, dot products, and cross products. So if you're not familiar with vectors, I would highly suggest you go to the pre-calculus videos in the pre-calculus stream on the Project Explained YouTube channel and review that. Also, you need to have a basic understanding of calculus, including how to take a derivative and how to take an integral of basic functions, including polynomials and trigonometric functions. So once again, if you're not familiar with that, I would encourage you to go onto the Project Explained YouTube channel and review that before beginning this lesson. So we'll do a very brief review of vector operations. So the two that I'm going to be talking about are the scalar or dot product and the cross product. So at the top of the screen, you can see the cross product, which is the vector product. So the cross product is a vector product between two vectors, and it outputs a vector as well. So the cross product u cross v would be represented as the determinant, with the first row being the unit vectors I, j, and k, with the subsequent rows being the components of the vectors a, b, c, and d, e, f. So the cross product outputs a vector that is normal to both of the original vectors, as well as with magnitude equivalent to the area of the parallelogram spanned by these two vectors. The perpendicular and magnitude portions of this are not too important right now. They will become pretty useful in the rotation unit as well as in E&M, but for now, just understanding how to calculate the cross product as well as some basics about the concepts behind it is enough. Just briefly to review, some examples of vector quantities are position, velocity, acceleration, and forces. And examples of scalar quantities are speed, work, and energy. So the scalar product, or the dot product, is the second product on the left side of the screen. It's between two vectors again, but u dot v is the scalar product, so you multiply the respective components of each vector with each other and then add them together. At the bottom over here, there's a diagram of head to tail addition of vectors. That's the graphical way that we add vectors together, with a plus b being the head to tail sum of the original vectors a and b. So first, we're going to go through some conceptual questions. So first of all, what angle between two vectors results in the scalar product being a maximum? So when theta, the intermediate angle, is 0 degrees, the scalar product is a maximum. That's because the scalar product can also be rewritten in trigonometric form as the magnitude of u times by the magnitude of v times by the cosine of theta, with cosine of theta being a maximum when theta equals 0. So what angle between two vectors results in the magnitude of the vector product being a maximum? So this would be theta is 90 degrees. Because once again, the cross product, or the vector product, its magnitude can be written as the magnitude of u times the magnitude of v times by the sine of theta, with sine of theta being maximized when theta is equal to 90 degrees. So we already wrote for number 3 the trigonometric expressions for the magnitudes for both of them. And for the magnitude of vector AB, once again, just for review, we just look at Pythagorean theorem. So we have A and we have B. So the magnitude of this vector would be the square root of A squared plus B squared. Just review from Pythagorean theorem. So one portion of kinematics that we need to look at is the calculus of vector functions. This overlaps with math a little bit, but it is something that is important in physics, as a lot of times we can represent complex motion in terms of time using vector functions. So all of these vector functions are parameterized in terms of time. So in addition to the appropriate position, velocity, or acceleration value being assigned, you also have a time value, which would be the independent variable in this case. So the position vector can be written as x of ti plus y of tj plus z of tk. And the velocity vector is defined as the first derivative of the position vector. So you just take the derivative of each component separately. as you can see in the red box. And the acceleration is the derivative of the velocity vector, or the second derivative of the position vector, once again taking the derivative of each component separately. So, and just to recall, remember that the derivative of a constant is 0, and the velocity vector v, a definition that you should know is that the velocity vector v is always tangent to the curve r. So an infinitesimally small increment in the curve length is in the direction of the velocity vector, and we're going to use that fact in a second when we do our example problem. The other thing that you should know is that the speed is the magnitude of the velocity vector. So in addition to finding the velocity vector, once we have that information, we can calculate the speed, which is the magnitude of the velocity vector. So let's go through example number 1. So we have this vector function. So first we want to find v and a. So in order to find v first, we have to take the derivative of r, each component separately. So v, the derivative of the first component, well, the derivative of cosine is negative sine, and from chain rule, we have to multiply omega out to the outside. So we get negative omega sine of omega t times I hat. For the second component, the derivative of sine is cosine, but once again, chain rule, we have to multiply the omega to the outside. So omega cosine of omega t j hat. And then lastly, the derivative of t with respect to time is just 1, so plus k hat. So acceleration is the derivative of velocity. So now we need to take our velocity vector and differentiate each component of it in order to find the acceleration vector. So once again, the derivative of sine is cosine, and once again, chain rule, multiply the omega out to the outside. So you get negative omega squared cosine omega t times I hat. For the second component, we get that the derivative of cosine is negative sine. Once again, multiply the omega to the outside by chain rule. So you get negative omega squared sine of omega t j, and the derivative of a constant, which in this case would be the vector constant k, is just 0, so it's negligible. So one thing to note here is at least in the x and y directions, we can see that a is equal to negative omega squared r. And that's a result that we're going to become more familiar with as we look at uniform circular motion, and especially during the unit of simple harmonic motion. So that's something that is a bit of a preview for the future. So part B, find the magnitudes of them. So for the magnitude of the velocity vector, it would be the square root of each component. So it'd be omega squared sine squared omega t plus omega squared cosine squared omega t plus 1 squared, right? And then this portion over here just becomes omega squared, because sine squared plus cosine squared by Pythagorean identity is just 1. So then for the magnitude, we get the square root of omega squared plus 1. Because of course the 1 squared is just 1. And for the magnitude of A, we have that A magnitude is equal to omega to the 4th cosine squared omega t plus omega to the 4th sine squared omega t plus 0 squared. So we get it's a square root of omega to the 4th, once again using Pythagorean identity, and then you get the square root of omega to the 4th, which is equal to omega squared. So for the last part, we have to show that A is normal to the curve R. So this is using the result that I mentioned earlier, which is at an infinitesimal increment in the length of the curve R, so basically the arc length, is in the same direction as the velocity vector. So in order to show that A is normal to the curve R, we need to show that A dot V basically is equal to 0, because based on the trigonometric form of the scalar product that we looked at earlier, we saw that it was the magnitude of u, magnitude of v, cosine of theta. So cosine of theta is 0 when theta is 90 degrees. So if the dot product is 0, then we can show that they're perpendicular to each other. And just looking at the components which we derived, you would get negative omega sine omega t, negative omega squared cosine omega t, so that'd be a positive, and you would have the same magnitude but opposite direction for this component because it would be negative. So this all wipes out to 0. So it is verified. So here's a short multiple choice question quiz. So use these to test your knowledge of vector functions and the calculus that relates them to each other based on what we just studied. Okay, I'm hoping you're back and you knew how to solve the problems. So for question number 1, we are asked to find the x and y components of the instantaneous velocity. So we have the position function. So we need to differentiate each component to find the velocity vector. So this one is a little easier because it's just polynomial. So the derivative of 8t squared is 16t, derivative of negative 4t is negative 4 times I. And then for the j component, the derivative of 2t cubed, that'd be 6t squared, minus derivative of 3t squared would be negative 6t, because we have the negative sign there, plus 6. Derivative of 6t is just 6 times j. So then we have to plug in v of 2, since we're being asked for a numerical value, and get 32 minus 4 I hat plus 24 minus 12 plus 6 j hat, which simplifies down to 28 I hat plus 18 j hat meters per second. So the correct answer should be B. So for question number 2, in another scenario, the acceleration of a vector of a particle is given as the equation on the screen. What is the magnitude of the particle's velocity? So for this one, we don't actually have enough information to choose because they haven't mentioned what the initial velocity of the particle was. So when we carry out that integral, we only know what the change in velocity was over the time period, but we don't know what the particle's actual velocity is because of that plus c. So we don't know what the initial velocity was, so there's not enough information to choose an answer. So when acceleration is uniform, so when it's a constant value, there are some equations that we can use which have derivations on the screen. So we know that just from the definition of velocity and acceleration and the relationship between them, that v of t is equal to the integral of a dt, which would be equal to at plus v naught, v naught being the constant of integration here, which is the initial velocity. Using that equation, then we know that the position as a function of time is the integral of velocity. So that'd be the integral of v naught plus at dt. And then once again, we'd get v naught t plus 1/2 at squared just from the integration of polynomials. And then the constant of integration would be x naught, which in this case is the initial position. Another really important constant acceleration equation that we want to use is the one that relates the velocity, acceleration, and displacement. So the derivation of it is right over here. So we know that the displacement is equal to, when acceleration is constant, is equal to the average velocity times by time. So we know that the final velocity plus the initial velocity over 2 is that average velocity times by the time, which in this case would be the final velocity. So basically the change in velocity over the acceleration. You can check and make sure that the dimensions work out for yourself, but you should get meters per second over meters per second squared, so you get seconds. So everything checks out there. So you get vf squared minus v naught squared over 2a. And then just rearranging the equation, multiplying 2a to both sides, you get vf squared minus v naught squared is equal to 2a delta x. So that's another one of the important equations that we're going to use. And it's really important that you understand, especially in AP Physics C, because there will be situations where the acceleration is variable and time dependent. These equations only apply when a is constant, which includes both magnitude and direction. Okay, so let's look at example number 2. So a runner is moving in the positive x direction and passes the origin at time t is equal to 0. Between t is equal to 0 and t is equal to 2 seconds. The runner has a constant speed of 8 meters per second. And at time t is equal to 2, they begin accelerating at a constant rate of 4 meters per second squared in the negative x direction. And we want to find the runner's location at t is equal to 5 seconds. So it's for a situation like this where there's a section where there is an acceleration and is not an acceleration, or the magnitude of it is changing between two time intervals, but within those time intervals it's still constant. Let's break it up into two intervals, and then we can just add the displacements together. So for the first interval, it's super easy to find. We know that delta x, in that case, there's no acceleration, so it'd just be v naught into t, which in this case is just 8 times 2, which is equal to 16 meters. In the second interval, delta x2, so then we do have an acceleration. So we have the same initial velocity, that would be 8 times 3, with 8 being the initial velocity, times t, minus 1/2, minus, because the acceleration is in the opposite direction, towards the negative x-axis, minus 1/2, the acceleration was 4 meters per second squared, times by t squared, which would be 3 squared in this case. So that'd be 24 minus 1/2 times 36, which would be equal to 6 meters. So then adding them together, the delta x total would be 16 plus 6 is equal to 22 meters. So in addition to 1D kinematics, a big part of kinematics is 2D kinematics, and the most common form of 2D kinematics in AP Physics C is projectiles. So one thing that you should always remember whenever you have any multi-dimensional kinematics problem is that the x, y, and, if applicable, z components of motion are independent of each other. So motion in one dimension doesn't impact motion in another dimension. So looking at the diagram on the screen, we can see the path of an ideal projectile. So it's launched with initial velocity vector v with a certain magnitude and direction. So the direction is indicated by the angle theta. So in order to find the equations of motion for each of the dimensions, we want to find the initial velocity and then identify if there was an acceleration in that direction. So starting in the x direction, it's really easy. The velocity initial in the x direction is just v0 cosine of theta, just using the trigonometric relationships that we have. We know that we have theta and we have v, so this vx, the cosine of theta would be equal to vx over the initial velocity. So vx is equal to the initial velocity times by the cosine of theta. So also in the x direction, we obviously don't have any acceleration. We're neglecting air resistance in this case, so there's no acceleration, so it's very simple, just the initial velocity times by time. The y direction, similarly, we can find the initial velocity as v0 sine theta, because the sine of theta would be vy over v naught, so vy would be equal to v naught sine theta, and then we multiply that by t for the first part of our kinematics equation, but we do have an acceleration in this case, so minus 1/2 at squared, minus because the acceleration, which is the gravitational acceleration, is down, whereas the initial velocity is upward. So we're establishing upward as positive and downward as negative. So we have minus 1/2 gt squared, where g is the gravitational acceleration in free fall on Earth, which is equal to 9.8 meters per second squared. So just some conceptual questions to evaluate. What are the x and y components of the velocity at point A? So at point A, we would consider that it's still moving with horizontal velocity, which would be v naught x, which is equal to v0 cosine of theta. But at A, because in the y direction it's changing directions, vy is equal to 0. So it only has an x component of velocity at that point. And how much time does it take for the projectile to reach point B versus point A? You could verify this mathematically, but for an ideal projectile, the path traveled for the first half and the second half is completely symmetric. So the magnitude of the velocity at the initial point and the magnitude of velocity at the final point is the same, the speed is the same, and the path is the same. So the time it takes to get up here is the same amount of time as it takes to go down here for an ideal projectile. So the amount of time it takes to get to point B is twice that it takes to get to point A. So here are some useful ideal projectile results. So first of all, just remember that you can only use these results when the projectile is not being launched from an initial height. If it is being launched from an initial height, then you just have to go through and solve the quadratic equations manually. But if it's an ideal projectile result, we can use these formulas to get information such as the range of the projectile or the maximum horizontal distance that it travels and the maximum height really quickly. So for the range formula, what we want to do is find the time at which the projectile hits the ground. So we set y of t equal to 0. Solving for that, we get t is equal to 2v0 sine theta by g. And then we're going to plug in that time value into the x component of position in order to find the maximum horizontal distance it travels. So x of 2v0 sine theta by g would be equal to v0 squared sine 2 theta by g. So that's the range of an ideal projectile. For the maximal height of an ideal projectile, what we want to do is find the time value at which the projectile's y velocity turns to 0, which indicates that it's changing direction, which indicates that it's at its maximum height. So we take the derivative of the y component, so vy, which would be v0 sine theta minus gt, we set it equal to 0. We get our time value, which is v0 sine theta by g, and then we plug that in to the y expression to find that maximum height. What we end up getting is v0 sine squared theta by 2g. So that's the maximum height. So example number 3 is asking us to find the angle for which the range of an ideal projectile is equal to the maximum height. So in order to do this, we need to set the range equal to the maximal height. So we get that v0 squared sine squared theta by 2g, which is the maximal height, is equal to v0 squared sine of 2 theta by g. So v0 squared obviously cancels everywhere. Sine squared theta, we're going to leave that how it is. And we're going to expand sine of 2 theta using double angle identity into 2 sine theta cosine theta divided by g. So we're going to multiply both sides by 2g. And in that case, we're going to get that sine squared theta is equal to 4 sine theta cosine theta. Dividing both sides by the sine of theta, we get that sine theta is equal to 4 cosine of theta. And bringing that back up here, that we divide both sides by cosine, then we get that the tangent of theta is equal to 4. At this point, we need to use a calculator and find that theta is equal to the arctangent of 4, in which case we get that theta is approximately 75.96 degrees. So this is a very common type of question that you could be asked, where it's very useful to have these ideal projectile results ready, because otherwise it would take a long time to get the answer to this kind of a problem. But using our results, we got the answer super fast. So there are a few more complex types of problems which I want to briefly discuss. So the first is an inclined plane problem. So you're going to look at inclined planes a lot when you get into forces and dynamics, but you do need to know a little bit about them during kinematics. So this is an inclined plane, and it's frictionless, and the coefficient of restitution is 1. So anything that's on it, it's not going to lose any energy through collisions with the incline. It's inclined at an angle of theta, and we have a ball or something that's being launched off of it with initial velocity v. So with these kinds of inclined plane problems, they're very similar to general projectile problems. There's just one modification that we need to make. We're going to tilt our axes. So we're going to consider that the plane itself, so the parallel to the incline, is the x-axis, and then perpendicular to the incline is the y-axis. So then from there, we need to dissolve the gravitational acceleration. So the component of gravitational acceleration, which we would now consider in the y direction, would be g cosine of theta. And the gravitational acceleration component in the x direction, which now we do have an acceleration in the x direction because we tilted our axes, would be g times the sine of theta. So once again, from here, you can apply your kinematics equations in the same way that you would for a general projectile problem. The only difference is now the x component of position and velocity isn't going to be as simple because you have an acceleration now, this g sine theta. But other than that, the procedures are very similar. The only difference is now, because this isn't an ideal projectile, you have to do all of the work solving the quadratic equations on your own. You can't use the nifty range and maximal height formulas that I mentioned earlier. Some other facts that you should just be aware of is that the time between each bounce is the same, because as the ball, for example, bounces down the incline, even though the horizontal speed is increasing, the vertical speed at each bounce is remaining the same. So the actual y portion, y of t, the path every single time vertically for each bounce is the same. That's not the same for the x component though, which is why the distance between each bounce horizontally across the plane increases. So that's just something to be aware of. The other very common type of problem that you'll have is a running problem. So you will have a projectile being launched, usually it's an ideal projectile, to some distance, and you'll have a person who's trying to catch that projectile right as it hits the ground. So for those kinds of problems, what you want to do is find the range of the projectile, based on finding the range of the projectile, figure out how far that is going to be away from the person, right? And then based on that, you can find what speed the person should be traveling with in order to reach this point exactly when the ball hits the ground. So that's another very common setup that you have for these kinds of problems, which not only uses the knowledge of projectiles, but then also you have to do additional calculations and applications for 1D kinematics with the person running towards that point on a 1D kind of situation. So that's pretty much it for today. So thank you so much for watching this intro video for AP Physics C Mechanics. So feel free to look in the comments section. There will be a practice multiple choice quiz attached in order to test your understanding of the chapter. And I would highly recommend rewatching this video if there were any parts of it that you felt first time were a little unclear. Rewatching and slowing down can really help digest these physics concepts more. And the next video, which will be on forces and Newton's laws of motion, will be coming soon.